So here was an area of 8 meters squared. We have a length of 12 centimeters. We can convert immediately and say 0.12 meters. We have a thermal conductivity of 0.050 watts per meter Kelvin. We have a temperature of the lower temperature region being negative 15 degrees Celsius, or we can say 258 Kelvin. We have the temperature of the higher temperature region is 22 degrees Celsius, or 295 Kelvin. And this is runs about 15% of the time. Now, let's separate the givens. We have a exhaust energy per unit time. This is going to be equal to Ka T sub H minus T sub L over L. So we can say that the coefficient of performance is going to be equal to Q sub L over W, and we can say that this is going to be Q sub L over T, and we can say W over. Now, T, it can't be only T, it has to be 0.15 T, because again, this is only running 15% of the time. And this will equal T sub L over T sub H minus E sub L. So using this, we can actually relate and say work over time, or power, is going to be Q sub L over time divided by 0.15, and this will be times T sub H minus T sub L divided by T sub L. And we can substitute for Q sub L over T and say that this is going to be equal to K, the thermal conductivity, times the area, times the higher temperature region minus the lower temperature region, divided by 0.15 times the thickness, and we'll have times T sub H minus T sub L divided by T sub L. And we can finally substitute, so we'll have 0.05, the thermal conductivity, times 8, the surface area, times 295 minus 258, all divided by 0.15 times 0.12. And then here we'll have, again, 295 minus 258 divided by 258. And we're getting a power output minimum of 118 watts. So this will be our minimum power output needed. Again, the answer is 118 watts. That is the end of the solution. Thank you for watching.